Second grade debate. I love sitting in.
So here's your homework for due on Friday. So the first one is actually kind of this is kind of a classic. You will see this in other classes. This is called the Cantor middle third set. Anybody ever heard of this before? So here's what you do. You take the interval from 0 to 1. And the first thing you do in the first step is you jerk out the middle third of it, the open interval, right, from 1/3 to 2/3. Now what's left over is 0 to 1/3 inclusive, and then 2/3 to 1 inclusive. So that leaves you 2/3 what you started, right? Then in the second step, you got these two blocks, these two little subintervals. You pull out the middle third of those. So once you've done that, now you've got 4 intervals, right? Each of length 1/9, right? Now you pull the middle third out of those, right? Now you've got 8, each of length 1/27, and so forth and so on. So you pull out a third, you pull out the middle third of what's left over, you pull out the middle third of all the ones left over, et cetera, et cetera. Show that the total length of what you removed from this is 1. Right? So the length of the original interval from 0 to 1 is 1. You pull out a third, then you pull out, a third of each of the 2 pieces left over, then a third each of the 4 pieces left over, and so forth and so on. Show that the length of what you removed is 1. However, C, set that's left over. And let me tell you some stuff that'll be left over. 0 will be left over, right? You never pull out 0. You never pull out 1. You never pull out 1/3. You never pull out 2/3, et cetera, et cetera. What is left over is the same size as the number of points at 0 to 1. Even though the length of what you pulled out is the same length as the original interval, what's left over is the same size. This is actually rather surprising when mathematicians first discovered that this could be done. So my hint, doing part A shouldn't be too difficult at all. In fact, all you do is sum the geometric series. That should be easy. How do you show that what's left over is that size? The easiest way, arguably, to think about this is think about it this way. When you pull the middle third out of the original interval, what you're doing is think of everything as a base 3 decimal expansion, right? So instead of base 10, you do it in base 3. So the first 1/3 is everything that begins with the decimal 0. The second 1/3 begins with 1, and the third begins with 2. When you pull out that middle third, you're basically pulling out almost all elements that have beginning decimal 1. When you pull out the middle third of what's left over, you're basically pulling out everything that has second decimal 1, and so forth and so on. So think of it that way, and you might be able to show that what's left over has the size of the interval 0 to 1. Number 2, I think is actually not terribly difficult. You want to show that if you take the integers, union the interval from 1/4 to 3/4, union the interval from -3/4 to 1/4, that's the same thing as size-wise as the interval from 3 to 5. I would use Cantor, Frederick Bernstein. Number 3, there's too many words there, lots of words. It's not so bad. Recall earlier we obtained, if this is the set of functions from the reals, we considered equivalence relations by declaring the difference is, we say that F1 and F2 are equivalent under continuity if their difference is continuous. We say that they're equivalent D if their difference is differentiable. We had these equivalence classes. I believe that we've already showed that there's an onto function from here to here. By the way, with this problem, you can use any of the previous stuff in the previous homeworks. Just reference it. Tell me what you're talking about. I just reference it. You already know that there is a onto function from ED to EC. I think that was one of, maybe not last homework, but I think the homework before that. So that's part of what you did. There's an onto function from ED to EC. show that there's a one-to-one function in the other direction. Let me give you a little hint for this one. The way to make this easy is to abstract it, right? So I would prove the following little lemma. If you have a function from A to B that is onto, then you have a function from B to A that is one-to-one, right? Prove that lemma first, and then this will be immediate, right, by using the previous homework. Why is this problem even on there? Because when you, to do that little lemma, if there's an onto function from A to B, and there's a one-to-one function in the other direction, you need to do choice, the axiom of choice, right? So that's probably come on. Okay, I don't think that's too taxing. I hope, any questions on that before we get rolling? Okay, so the last thing we'll talk about are groups. And I appear to be kind of ahead of the curve, so I'm gonna go off notes, but I'm gonna do a kind of a big example. I'm gonna focus on examples of groups here for a little while. Here is a group. One can argue that when I teach you about the group, I'm teaching you about all groups, because this one sort of incorporates stuff. So this is a very, very large class group. One can argue, like I said, that if you understand these groups, you kind of understand all group theory. Because it turns out that every group can be realized as a subgroup of these. Sn is the collection of functions one-to-one. So this is the collection of functions that go from the set 1, 2, 3 all the way at the end to itself. These functions have to be one-to-one and onto. Now, this is going to be my group. It's certainly a non-empty set, right? Because there are certainly functions that go. In fact, what's one function from here to here that's one-to-one and onto? Thank you, right? It's a math class. You always do the easy thing first. The identity is certainly a one-to-one and onto function, right? So there's stuff in here. Right? How do you suppose that we combine functions? How can I combine two functions that are one-to-one and onto and get a new function that's one-to-one and onto? Yeah, that's right. We can compose it. Oh, you know what though? I bet even from your experience, even in calculus, when you compose two functions, do you get the same thing if you compose them in different directions? Maybe not. I would expect this to not, I would expect F composed of G, not necessarily be G composed of F. Right. Well, let's see here. What do we got to do? When I combine two functions, it still needs to be in Sn. Well, Well, that's one of the theorems we already know from class. The function is by, if two functions are bijective, their composition is bijective. So we went on that, okay? Function composition. Is it, associative? Yes, so you remember back, we proved that, actually what we proved is composition of relations is associative, and so functions are as well. Okay, what else we got? The identity function. What is the function that you can compose with any function and it doesn't do anything? Daniel, I need help. The identity function, right? And what is true about bijective functions? They always have an inverse, don't they? Okay. True. Let me give you a concrete example. Let's look at S3. But in our exploration space, S3, I think we're going to see that we really need to. Okay, first question. Okay, this is a good one. How many, in fact, let's just do this first. How many bijective functions are there? This is kind of a good warm-up counting problem. What's that?
In factorial.
Where do you get in factorial?
Because first, you have to map first element to one of the n elements, second one to one of the n minus one elements.
He's exactly right. Y'all see how that works? So you're going from 1, 2, 3. So one's got to go somewhere. How many choices does it have? Well, n. Now you've made that choice. How many places can 2 go? Well, it can't go to whatever the first choice is, but you've got complete freedom on everything else. How many places can 3 go? Well, anywhere but the previous 2. And so this gets out of hand pretty quickly, right? If n is 10, that's already a humongous number, right? I mean, if n is like 6, right, it's already 720. Let's write S3. So there's going to be 6 of these. Okay. So I'm gonna this is going to be kind of an exercise in saying we've got to invent something better. Okay, let me systematically go through it. Well, 1 could go to 1, 2 to 2, 3 to 3. I will call this one F1. Okay. If 1 goes to 1 again, I've got another choice. Now I can swap out 2 and 3. Agreed? I'll call that F2. Looks like I've exhausted all possibilities where 1 goes to 1. So let's explore 2 goes to 2. There's one of them. The other one has to swap out 1 and 3. I'll call that F3. Agree? And I guess I could make 3 stand to itself. I'll call this one 4. I have exhausted all the possibilities where at least one element is fixed. So the only other alternative is for them all to be scrambled up, right? So I guess I could take 1 to 2, 2 to 3, and 3 back here. Or I guess I could go 1 to 3, 2 to 1. I call it F6. Would everybody agree that that's an exhaustive list of all bijections? Well, let's get some practice. Let's compose some of this stuff. Huh. Let me be careful. This means that I do F3 first, right? So let's use our diagram here, figure out what happens. What happens to F in F3? Let's just kind of do this. When I plug in 1, it goes to 3, right? And then F4 does its magic, it goes to 3. So 1 goes to 3. Want to see how it goes? Where does 2 go? Well, first 2 goes to itself, and then F4 does its magic, so it goes to 1. Where does 3 go? This composition has to be a bijection. So 3 has to go to 2. No two ways about it. But hey, this is me talking, so we better check it, right? I may have screwed something up, and if something goes wrong, that means one of my others is probably wrong. Let's see what happens. When I plug in 3, it goes to 1, and then on to 2. Okay, good. So this turns out to be, what does it turn out to be? F5? No, F6. Everybody okay with me? I'm curious. What happens if we do this in the other order? Right? Okay, we start 1 goes to 2, and then to 2. Where does 2 go? I'm doing F4 first. It goes to 1, and then 3. And 3 better go to 1, but we'll check it. 3 goes first to 3, and then moves on to 1. This one is F5. Everybody okay with that? By the way, what do you suppose the inverse of this is? Every element of the group has its inverse. Let's see what it is. Itself, right? Think about what this has done. It's just swapped 2 and 3. How do you get back to where you started? Swap 2 and 3 back. Notice this one, and this one are their own inverses because what you've done is a swap. What do you suppose the inverse of F5 is? It's F6, right? Think of 1 goes to 1, back to 1. 2 goes to 3, back to 2. 3 goes to 1, back to 3. And the other order, the other direction works as well. Okay. So if you're only swapping 2, yes, right? But if 3 is kind of a special case. Now, here's a takeaway. Wasn't that a fun example, right? You can get our hands dirty and see what's going on. Can anybody explain to me why I did S3 and not S7? We don't have an expect. I mean, I would have to write down I would have to write down a column 1 through 7 and a column 1 through 7 5,040 times, right? I don't have that kind of patience. So I would like to invent a new notation here. Cycle notation. I am going to rename these functions according to their notations. I'm just gonna call this E for identity. Right, nothing's changed. I'm gonna write this 2, 3. This notation means 2 goes to 3 and 3 cycles back to 2. There is no 1, that means it's left. Following this pattern, this will be 1, 3. 1 goes to 3, back to 1, 2 is left alone. This notation, what do you, how am I gonna write this one? Good. How about this one? Where does 1 go? Goes to 2. 2 goes where? Huh? And 3 cycles back. This one, 1 goes to 3, 3 goes to 2. This allows me to conveniently write E. I did say S7. So for example, let's practice a couple of these. Don't worry, I'm not going to do this 5,040 times, but I want you all to help me out. Well, there's well, one more than 7 person. Somebody's gonna have to share. Somebody tell me, where do you want me to send 1? 5. 5. How about 2? 3. You are psychic. Okay, 3. 7. 4. 1. Okay. 5. 6. We're running out of choices on 2. Okay, how about 2? And 7 goes to, I don't have to ask for that one, right? So what would this look like? Where does 1 go? It goes to 5, which goes to, which goes to, which goes to, which back go to. Let's do a couple more examples. Sometimes that's a bijection as well. Let's see what this one. I'm gonna call this a G, just for fun. And we'll call this an F. And then I'll multiply these. Let's see what G looks like. 1 goes to, which goes to 4, which goes to 1. So that one's cut off there. 1 goes to 3, 3 goes to 4, 4 goes to 1. What do I do now? Well, just to be organized, what's the smallest number that I have that's not accounted for yet? 2, right? Let's just pick it up at 2. 2 goes where? 5. 5 goes to 7. 7 goes to, closed off again. And where does 6 go? 6 goes to itself. So if you want to be really careful about it, you can do that. But often what happens is you just leave that out because that means any numbers left out means they go to 7. Okay. Small. Now, let me write G. 4, 2, 5, 7. And F. 1, 5, 6, 2, 3, 7. 4. Now here's what I want to do. Now remember what this is function composition. So that means even though F is on the right, it goes first, right? It's just like if you have the function e to the sine x. You plug in x to the sine first and then take the exponential. So we're going to do it that way. I just start with 1, this is the first number. Where does 1 go? It goes to 5, then to 7, and then it's done. Where does 7 go? To 4, to 1, and it's done. That's it. We can pose this way. 7 takes a trip to 4, then 4 is left alone, and then 4 goes to 1, and that's the end of the row. Okay, what's the smallest number that I've got that's not counted for? 2 again. So let's see what happens to 2. 2 goes to 3, to 4, and it's done. Where does 4 go? To 1, no 1, to 3. Where does 3 go? 7, to 2, and it's done. Oh, there we go. Okay, smallest number not accounted for looks like 5. See what happens to our friend 5. 5 goes to 6, and then no more 6. So there we go. Where does 6 go? It goes to 2, to 5, and it's done. 1, 2, 3, 4, 5, 6, 7, and that's it. Let's do it the other one. See what happens to F G. I bet it's there. Okay, where does 1 go? Let's just start with 1. It's the smallest number. No 1. 1 goes to 3, 7. 7 goes to 2, 3. 3 goes to, there's the first appearance goes to 4, to 1. Okay. First unaccounted for number is 2. 2 goes to 5, 6. 6 goes to 2. One, 2, 3, 4, I guess we've got now. 4 goes to 1, 5. 5 goes to 7, to 4. What's it 7? Right, okay with me?
How do you do this with a second in like
This right here?
yeah, how to do this?
Okay, so we start with 2, right? 2 goes to 5, no 5, on to 6.
Oh.
That, okay,
Six goes to
right. Anytime there's a, so I want you all, let's take a minute, you all practice this one. So example. take a minute and see if you can pound this out. This is an S9. That's exactly right. So you might think of it as composing all of these cycles.
Does it matter where F starts and G ends?
No, that's a great point, right? The way that we were doing this problem is this part was the G and this part was the F, and then we turned it around. But it really doesn't matter. This could be FGH, you know, so there's all kinds of ways you could think of it, and it doesn't matter. Let me point out that this algorithm always, notice that within each cycle, it's impossible to ever repeat a digit. Right, and in fact, right, so this cycle, what this does is this actually shows that any cycle can be, or I'm sorry, any one of these elements can be broken down. So let me clarify what I'm saying here. In the original FG here, there were multiple ones, multiple fives, right? You've got numbers in common. What this algorithm does is it takes this complicated composition and it rewrites it into smaller cycles where no numbers are repeated. And in fact, you can write down what this is. If you're still old fashioned and like this kind of thing. What did this one turn out to be? Well, this meant 1 goes to 7, and 7 goes to 1. 2 goes to 4. 4 goes to 3, and 3 goes to 2. And 5 and 6 are swapped. That's what that bijection is. Okay, let me give this one more minute, see if you guys can figure this one out. Where did you get 1 to go? 2.
Oh, actually, never mind. 5.
No 1. Oh, first 1. 1 goes to 5. On to 8. And no more 8s. So that's where it's journey ends. How about 8? 8 goes to 9. To 4. To 2. To 1. How about the math? Right. First number that I haven't seen yet was 2. Where does 2 go? 4. 3. 4. 1. 3. Looks like me. How about 3? 8. 9. No more 9. So how about 9? Where does it go? Channel Dolly Parton. Right, Dolly says that 9 goes to 2 to 5, 9 to 5. How about? What 5, where's that?
So,
7, and then it's done, isn't it? How about 7?
no, it's fine.
So-
Oh, never mind.
How about 7, where's it go?
4.
Agreed. 2, 4, 6, 8. Where's 4? Looks like it goes to 2. Let's check that. 4 goes to 3, 2, 3, 1, 2. What's the slide? We don't have all the numbers yet. 2, 4, 6, 8. What's the only number we've got left? 6 is the only one that's left out, and it better go to itself, and it does, because there's no 6 up there. Everybody okay? Yes.
So for the 5, 7, 4, we went from 5 to 7, or like the second to last one, we went to 5 to 7.
Uh-huh.
And then we circled from 7 to 1 in that same bracket.
Well, 5 goes to 7, and there's no more 7s. So that's the end of the journey of 5 in this one. Now pick it up in 7. 7, well, this is the first appearance of 7. 7 goes to 1, to 4, and that's the last appearance of 4, so there you go. And then 4 back to 2. Everybody okay with that? Let me show you kind of, here's another. Here. I think the Pentagon's sort of random. This will work for any Pentagon in 3 or greater. Actually, sort of works for 2 too. So I'm going to attempt to draw sort of good looking regular Pentagon here, hopefully. Let's assume that this is regular. How many symmetries are there on this? What do I mean by symmetry? Imagine that this is a piece of the puzzle, right in the middle of the puzzle, and I pull it out like a little kid's toy where they stick it in the Pentagon. How many different ways can I put that Pentagon back in? Certainly 5. Everybody agree? Because I can rotate this 5 ways. You're halfway there. You can also flip it over for everyone, right? So you can put it in 5 ways, and you can flip it over 5 ways. So there's actually 10 ways to do this, right? This actually forms a group. And I think of turning the Pentagon as and flipping it. So there are 2 things I can do. If I call this the y-axis, one thing is I can rotate 2 power 5. And notice doing that 5 times brings you back to where you started, right? And I can flip it. Y. I can think of this as a group, as function composition, right? I've got basically two operating functions. One that rotates, let's say clockwise, 2 power 5 radians, and the other one which is flipping around the y-axis. And I can do any composition, right? I can rotate it twice and flip it, and then rotate it backwards, right? By the way, What's the inverse of rotating at 72 degrees? Rotating it back 72 degrees or going full circle around, either way is okay. What's the inverse of flipping it? Flipping it again, right? So let's think about this geometrically. What happens if I flip, rotate, and flip? I'm gonna call it flip S, that's kind of what I'm saying. What happens, think of this as function composite. I flip my pentagon, I rotate it 72 degrees, and then clockwise, and then I flip it again. Anybody tell what I've done? What's in there? She's right, that's, you like geometry, didn't you? That's pretty good. I have to think about that a little bit more, but yeah, she's right? Because what, from your perspective, what she did, you rotate it 72 degrees, you flip it around the y-axis, so now it's over the other thing, and then, I'm sorry, you flip it, you rotate it, and then you flip it back. That's the same thing as rotating it backwards, right? Does everybody see that geometrically? This is a little group. It's got 10 things in it. Notice that when you do a flip and a rotation, it's not the same thing as doing the rotation and the flip. That's what this basically tells you. So this is actually a little group of 10 things in it. Now, I haven't completely freaked out because let me show you how you can do this in terms of this other stuff. Okay. Let's label this. Yeah, I'm going to call this 1, 2, 3, 4, 5. I'm just going to label the corners. Now, here is how I make this connection. When I move that pentagon, it forms a bijection of those 5 corners or 5 vertices, right? Can somebody tell me what is the rotation 72 degrees clockwise? What does that do? Where does that take 1? Right. And it takes 2 to 3, doesn't it? 3 to 4, 4 to 5, and 5 goes to 1. So I could write this way, couldn't I? I can interpret that rotation as the bijection of the starting points of those vertices to where they go, right? Yes.
So could you not write your Rubik's Cube problem the same way?
That's exactly. That's it. We're going to get to that. Yeah, you absolutely could. That's a great observation. How about S? What happens if I take this diagram and I flip it over the line or over the y-axis? What does it do to the vertices? Where does it take the vertex 1? To itself. That doesn't change. Where does it take 2? To 5, which goes back to 2. And it does the same, it swaps the other 2. You know, she figured out SRS is our inverse just by thinking about it. That's difficult for me. My brain pan works a little bit differently. That's why I had to use this the first time I ever saw the Rubik's Cube. I'm going to recover this thing right here. Let's look. Let's do this computation. Let's just compute it, the way we're doing it. Let's see what happens. Where does one go? Actually, you know what? I'm gonna crawl out of the box here. I'm gonna start at 5. When you do this computation, it doesn't matter what you start with. I always start at 1 just to keep track of things, but you can start wherever you want. It's arbitrary. I'm gonna start with 5 because it will help illustrate. Where does 5 go? Where does it end up? It ends up at 4. 5 goes to 2, on to 3, 4, and it's done. Where does 4 go? It goes to 3. 4 goes to 3, to 4, to 3, and it's. Where does 3 go? It does. 3 goes to 4, to 5, to 2. Let's see where 2 goes. 2 goes 5, 1. And then 1 better go to 5. It's always good to check. 1 goes to 2. 5. This was R. This is R inverse. Because R takes 1, 2, 3, 4, 5. This goes 5, 4, 3, 2, 1. Right? So you saw this geometrically, but the algebra actually just does it for you without having to think geometrically at all, really. Does everybody understand how to multiply these? And you're exactly right. So let me give you a practical example. Now, whenever you take a Rubik's Cube and you rotate it, what happens? Well, ask yourself this. How many pieces on a Rubik's Cube, I'm going to call these corner pieces, have 3 different colors on them? There are, I'll just call these something A, B, C, D, E, F, G, H. 8 corners. Now, when I scramble the cube, do you ever have a corner piece end up in the middle here? You got problems if you do, right? The corner pieces always go to other corner piece slots. So what you're doing when you rotate the cube is you're doing a bijection from the 8 corner places. You're doing a bijection of the corners themselves. That is an S8. How many side pieces do you have that have only 2 colors on them? Good. 12. That's an S12 there. And basically, you can write down things like this, number the side places. When you do a rotation like this, what happens? Well, if I rotate this, say counterclockwise, right, counterclockwise, then I get B goes to F, goes to G, goes to C. Right? And it does some other stuff to the sides. So if I write down what this is and I write down what this is and put them together, I can figure out what that does. This is how you can, this is actually just the beginning of it, but this is how you use symmetric groups to actually solve Rubik's Cube. There are other subtleties because you have to worry about orientation of the pieces. You can get to that later. Okay, hopefully that illustrates some practical groups for you. We'll talk more about the theorems next time. Any questions? Yes?
Would be like 6 functions and integers.
Well, Oh, right, right. Yes, that's right, because you can turn each of the 6 sides, but just by spinning the cube in space, you really don't have to concentrate on these sides. At a time. Okay, I will hopefully see you all in the math club today. It's gonna be a really good talk. It's about how to use ODEs to keep your goldfish from dying. So that's always fun, and the speaker's a really good one.